Hello, and welcome to my workshop and the BJT curve tracer sequence of labs. In this sequence of labs, you'll be analyzing, simulating, and assembling the subsystems of a BJT curve tracer. When complete, you'll have a device that can generate the characteristic family of curves for a BJT similar to the one I have on the oscilloscope right here. You might be asking yourself, what is a characteristic family of curves? That's a great question. Let's go over to the whiteboard and I'll explain. The characteristic family of curves describes the voltage-current relationship through an electrical device. Every electrical device, it doesn't matter if it's resistor, capacitor, diode, inductor, BJT, has a characteristic curve. In order to understand it, let's consider a thought experiment. So we take an arbitrary electrical component and we apply a voltage across it and we measure the current through it. And then we plot that locus of points. What would it look like? Well, let's take an easy example of a resistor. A resistor has a current voltage relationship described by a straight line. Why? Ohm's law. If we look at the slope of this line, it describes the change in current over the change in voltage. Change in current over change in voltage, which is the slope, is equal to 1 over the resistance. And since the resistance of a resistor doesn't change, the slope is constant. This will be an important idea as we explore the behavior of devices like diodes and BJTs. Now, since we got that, let's jump in and see what you'll be looking at this week in your lab. In this week's lab, you'll be given an unpopulated printed circuit board and asked to assemble the power subsystem and 555 timer subsystems. These are pretty easy to identify by the white lines on the printed circuit board. The board I have shown here is completely assembled. Please do not completely assemble your board this week. When you complete this assembly, your 555 timer will generate a square wave like the one shown on the oscilloscope above. Your waveform should look pretty similar to that, but it will differ in some key attributes. How does the 555 timer subsystem do this? Let's go back to the whiteboard and I'll explain. The essential elements of the circuit are shown up here on my whiteboard. They consist of an 8-pin dual inline package IC, solder in the socket and install the IC into the socket in case you need to replace it, a pair of resistors, a 100 nanofarad capacitor. Pro tip, 100 nanofarads is 0.1 microfarads. Make sure to get your units correct. And a pair of diodes. If we haven't covered diodes yet in the class, think of them as one-way valves for current flow given by the direction of this arrow. In this case, current can flow from the top to the bottom, but will be blocked from flowing from the bottom through the top. Likewise with the diode to the left. Now let's talk about how the circuit works and how it generates the output waveform. When you first power up the 555 timer, this capacitor is initially discharged, meaning the threshold voltage is at 0 volts VT, and that will cause the discharge pin to be electrically disconnected from this circuit. That will allow current to flow from the 9 volts through the 1K, through this diode, and allow charge to accumulate on the upper plate of this capacitor. That accumulating charge will cause VT to increase. When VT exceeds 2/3 of the supply voltage, 6 volts, this discharge pin, which had been electrically disconnected, will now internally connect to ground. That will allow the charges on the upper plate of this capacitor to flow through this diode, through the 10K resistor to ground. When that will cause the threshold voltage to decrease. When the threshold voltage goes below 1/3 of the supply voltage, 3 volts, the discharge pin will electrically disconnect from ground and from the circuit, allowing the charge sequence to apply again. Now, what does that have to do with the output? The output voltage is determined by which mode, charging or discharging, the 555 timer is in. While charging this capacitor, the output pin will be at 9 volts. While discharging the capacitor, the output pin will be at 0 volts. And this cycle of charge-discharge generates the square wave that you saw on the oscilloscope. Now, with that under our belts, let's go take a look at exactly what you'll need to turn in order to complete this week's lab. In this week's lab, you'll analyze the circuit using RC time constants, determine the amount of time it takes to charge from 3 to 6 volts and discharge from 6 to 3 volts. You'll next simulate the circuit using LT Spice and compare your results to your analysis in the previous step. And finally, you'll assemble. Again, please only assemble the power supply subsystem and the 555 timer subsystem. You'll compare the results of all three measurements and put them in a table and turn in all of your work as a single PDF. Make sure to include a sentence, English sentence, before each of the answers that you turn in. Every student builds their own board, but you may work in teams of two. Good luck and good hunting on this week's lab.